Buenas.
Hola.
Carlos, me comentaba Enrique si habíais mandado el enlace ya para la plenaria. O sea, el enlace me refiero a
Es el mismo.
para la plataforma.
Sí, sí, sí. De
Ah, vale,
hecho,
perfecto.
me han respondido ya ellos. Sí, sí,
Ah,
me
vale,
han
perfecto.
respondido ya que lo han recibido.
Bien, bien, perfecto. Hello.
Hello, can you hear me?
Everything. Yeah, I can hear you, but also all the people. Okay, so this is already posted in the platform. So we haven't started, but whatever we said here, people who is connected can listen. Okay.
Okay.
So everything good, Kundan?
Thank you.
Yeah. I know what I do.
I am
Okay.
very serious about it, you know.
I see. So everything good? Yeah.
So far, so good. Yes.
Good.
So, is it already live on YouTube?
Yeah. It's in the platform. So in the platform, the conference. I mean, we
Yes.
start at 4, but
Okay.
we put the link in advance, just that
Yes.
people is ready and everything. So
Okay.
be careful.
Okay. Okay. Good. So I can look at the YouTube.
Yeah, but after you look close, so that we don't listen to you twice.
I know. I will not do that actually. But anyway, let me first share my screen and then see whether
Yeah, we
things work.
can check. Yeah, that's
Oh, there is somebody sharing the screen.
Oh, yeah, Carlos.
Dime.
Sí, que Kundan es el speaker
Hola,
para
¿me
que pueda
escuchas?
compartir. Sí, ¿me oyes? ¿Me oyes, Carlos?
Sí, te escucho.
Sí.
Te escucho.
Vale, que
Okay.
vale, que quería Kundan compartir pantalla.
Yeah.
Todo suyo.
Vale, gracias. Okay, Kundan, you can try, I think.
Gracias. Yes. Gracias.
Good. So
Yeah,
do
is
you
it
want?
coming?
Yeah. Do you want to put it in full screen or because you are in the
Yes, of course I
iPad,
want to.
right?
No.
Oh. No,
I
okay.
am
No
on
iPad.
no iPad.
No complications.
Last time I did it at Siam Geosciences.
I was there, I
Oh,
remember.
you... Okay. Since then, I am not taking much chances.
Good.
Yeah, it is coming.
I think it's
Cool.
I think it's perfect. If you want to move or
Okay.
try, but I think it's good. Yeah, perfect.
Okay, perfect. Okay, good. I'm just hoping that there is no electricity outage and that kind of stuff.
I see. Well, we already had some trouble this morning in the platform, so I hope now we are good.
Okay.
I hope.
Okay, because so I am in an apartment. So here, when the electricity goes, it comes back.
Oh.
But in between, there would be 2 minutes of
break.
Because it takes time to get the electricity, and also the router will restart and so on.
Oh, yeah. I understand.
So that will be the key concern.
Okay. Well, we
Because
will
otherwise,
cross fingers.
Yes. Otherwise, it looks not too bad actually with the connection.
Yeah. I think it's good. Yeah.
Yeah, it's. We have taken a pretty nice connection. So in general, it should work. But
it should work, right? Yeah.
Yes.
Yeah, with these things, you never know. Yeah, it's.
No.
I came to the university because I was not sure that in home everything will work.
Okay.
And this morning I had some problems also with the internet here, but it was like very little, and then I could manage, so it was fine. But you never know. You come here because of this, and then maybe at the university there is a problem, and then
no place is safe.
Yeah.
Also in Bergen, I have troubles.
Yeah.
Yeah.
In the
Bergen,
university or at home?
Mostly I have tried at home, but at home I had several times issues.
Yeah. Well, we hope this is good. I think it will be fine. Let us hope.
So you are, as an organizer, doing okay with the conference? Are you happy with the way things are getting?
Yeah. Well, this morning we had some troubles with the platform, but with Jitsi, but now I think it will be fine. I mean, this will be fine because it's Zoom, so it's okay.
Yes.
And for the parallel sessions, I hope everything works. So,
okay. So do you know where this is going to be next year?
No, in fact, I think there should be, so it's a competitive call. So there are some proposals, and then the managing board of ECOMAS, they choose. So yeah, I'm not sure. I don't know even if the call was launched. I don't know.
Okay. But it has a good number of participants, it seems.
Yeah. We have around 270 registered participants, so it's it's quite good. We were expecting like 100 or something, and then we started to get abstracts, and it was like, whoa, it's good.
Yeah. I think the online has made it a bit easier for people to participate.
Yeah, people, I don't know if to participate or at least to register.
Okay.
It seems that you say, oh, yeah, I will participate, I register and everything. But then virtual is much easier than if you are at home and then you say, oh, today I am not feeling like listening to this. And... But we are happy with the numbers and everything. So I think it's been good. Okay. We are nice. 24. Regarding the questions, I will. So in the platform there is a chat, okay? Yes. But you don't need to check. So after the talk, I will check if there are questions in the chat, okay? And then I can read the questions for you, okay?
Okay. There is also a chat and there is also Q&A.
Yeah. That's it. Yeah. So yeah, there are some questions. I have opened the platform also, so it will be fine. Okay. So what time is now there?
It's 7:20 in the evening.
7:20. Oh.
Yeah, it's not too bad. You see the.
Okay.
Almost. The sun is almost going out.
Haha. Still light, yeah.
But there is still a bit of light. It is dark, not dark, but getting dusky.
I see. Dinner time or you there?
Yes.
What time do you have dinner there in India?
Yes, this should be around 8:30.
Around 8. Okay.
But somebody first has to cook. Huh?
I see. so it's good that your talk is at this time because then you will find the dinner done, right?
No, I doubt it.
Okay.
My wife and kid are away.
Oh, so you have to move for yourself.
Yes.
I see.
She went to a relative of hers.
Okay.
Yes. When she came to know that I'm going to have this conference for 3 days, then she says, okay, this
they
also
took advantage of disappearing. I see.
So tomorrow they will come.
Good.
Yeah, good. I will go and take them back.
Nice.
So let us see. So this is the last plenary talk, I think, no?
There is another one tomorrow.
Tomorrow, okay.
Yeah.
So there are 5 in total, or this is the third one?
This is the third one. There are 4.
1, 2, yeah, 1, 2, 3. Okay.
Yeah.
So this is not being organized by Zaragoza, yeah? It is organized by combination.
We organize 2 guys from Valencia and myself from Zaragoza.
Okay.
And but mainly they have done, because in principle it was gonna be held in Valencia at the university. Yeah. So then they did a lot of work. They did almost everything. So
yeah, it's nice to have this meeting. This is
but it's a pity.
It's a good meeting.
Yeah, but it's a pity that we cannot meet in person in
Yes,
Valencia.
Of course.
I was looking for going to Valencia also, but not possible. Yeah.
But I think things are getting now a bit better, no?
Well, I was hoping this, but now with I think people got relaxed, and also now with the end of the school year and the university year and everything, then people is going for holidays to the beach, and I think numbers are increasing now again.
Oh, really?
Yeah. Vaccination is going well, I think, but yeah, numbers are a bit worrying now, I think, again. But well, we will hope that everything stays stable.
But in UK, even if the numbers have gone up, the situation has not worsened. At least that's the understanding we are getting, no? I mean, in the sense of hospitalization and...
Yeah, well, that's true. There is more people which is vaccinated and yeah,
having less trouble.
Yeah. So yeah. But yeah. And what about there? In India, situation is better? It has improved?
Yes, it has improved so much that everybody is now out.
It's now, come on.
There is traffic jam and all sorts of crowding.
I see. So it's normal again.
Oh, it is again back to normal. Again, if it strikes, it will strike with vengeance. Again.
Oh.
Yes.
Oh.
I don't see it happening much differently from last time.
Yeah.
Yes. Because you see, I mean, I don't see, the kind of seriousness which one would have expected after second wave.
Yeah.
Including, I have to say, myself too.
Also, you are relaxed. I see.
So I am not behaving much differently from my fellow countrymen.
The rest of the... I see.
I mean, I am wearing mask, but I don't think that I'm really taking the kind of precautions I should have. I am more careful in Bergen.
Yeah, I can imagine.
Where the cases are much less.
I see.
In fact, I went to a couple of restaurants and so on. So a friend of mine is visiting me. So he was going to get tested. So I thought I should also get tested for all the things I have done. So we will know about it. I'm hoping that it should be okay.
I see. So you got already tested, yeah?
I haven't got the result yet.
Yeah, okay.
And I don't know how much time it takes before you get infection and you get positive in RT-PCR.
Yeah, this is when, I don't know.
So I think it is 2-3 days.
Maybe, I'm not sure, yeah. Okay, so you will tell me the news.
I will start, taking medicines or whatever it is supposed to be taken, just the moment I come to know that something has happened.
Oh, can you hear me?
Yes.
Oh, I think my internet cut for a second.
Oh,
I hope everything works. No, but it's fine now. It is fine, yeah. Okay. Some minutes more.
So you are at the university?
Yeah. In fact, I am in Paco's office.
Ah, okay.
Because in my office, internet doesn't work properly. So then
okay.
I came to the main campus, yeah. And then he gave me the key because he said, well, I finished with the exams and everything. So,
okay.
Yeah.
So he's not around.
I think, yeah, he's at home probably.
Okay.
He had to finish grading exams or
Of course,
something.
of course.
Thing. But
But you're also done with teaching and everything.
yeah, I only had teaching the first semester.
Okay.
So then this semester I was only focused on other research stuff and other administrative and these things that here in Spain we have to do a lot of things. But okay, what I did here. Minutes. Do you want me to tell you something after 45 minutes or something, or I think you have the time
I have
control, right? Okay, good, perfect.
This will tell me.
Good.
I also have a watch, so I'm watching.
Good. Okay. Okay, so I think
one moment. This will.
okay.
I will have to reshare because.
It blocked.
If you, yeah, if you do it. Yes.
Okay, perfect.
One moment.
Yeah.
One moment. Why is this?
Maybe remove full screen mode and.
Yes.
Okay.
Yeah.
It's good now? Okay.
Yeah.
Okay, so I think we can start. So hello, everybody. My name is Carmen Rodrigo from the University of Zaragoza, and I am one of the organizers of this GIG 2021 conference. I would like to welcome you to the third plenary session of this sixth ECOMAS Young Investigator Conference. And it is a great pleasure for me to introduce our plenary speaker today, that is Kundan Kumar. So Kundan did his master's studies in industrial mathematics between the Fraunhofer Institute for Industrial Mathematics in Kaiserslautern in Germany and the Eindhoven University of Technology in the Netherlands, where he also obtained his PhD in applied mathematics in 2012, which was titled Upscaling of Reactive Flows. After that, he did a 2-year postdoc at the Oden Institute in the University of Texas at Austin, under the supervision of Professor Mary Wheeler, one of the reference names in the field. And currently, Kundan is associate professor in the Department of Mathematics of the University of Bergen in Norway. And also he is a member of the Porus Media Group at that university, which is led by Professor Jan-Martin Norboten, and which is one of the strongest groups in the field of porous media. His research interests are related to the development of scale models and also numerical models for complex couple multiphysics problems related mainly with applications in porous media. He has published more than 50 research papers, and he has an impressive list of collaborators, which include the most renowned names in the field of porous media. Thanks to his outstanding contributions to the numerical analysis and computational methods for complex flow and transport problems in porous media, in 2017, he was awarded the SIAM Early Career Prize for Geoscience, and also the Lauritz Meltzer Prize for Young Researchers at the University of Bergen. So for me, it's a pleasure to introduce Kundan for his talk, and I am looking forward to your talk, Kundan. So whenever you want, please, the floor is yours.
Thank you, Carmen, for this very kind and generous introduction. I am very humbled and honored to be presenting at this meeting. I should thank the organizers for giving me this kind opportunity. The title is Coupling of Flow and Geomechanics in a Fractured Porous Medium. As you can see, the flow and mechanics, these are going to be the processes. They are going to be coupled. And the fractured porous medium, that is going to be the setting, the geometric setting in which we are going to study this coupled process. Now, why are we interested in this kind of processes? Now, anthropogenic activities, the activities which are done by the humankind, that involves the subsurface, typically that involves injection and extraction of fluids either into the subsurface or taking out from the subsurface, and sometimes both. On the right, you see you have different applications: oil, gas, carbon sequestration, wastewater, geothermal, groundwater, and so on, which take place at different depths. So groundwater, for example, is number 7 as the minimal depth, and then the supercritical geothermal resource, which is at the maximum depth of around 3.5 kilometers, and so on. So now all this injection and extraction processes lead to imbalance in the fluid in the subsurface region. That imbalance may lead to mechanical instabilities, which can be manifested in terms of induced seismicity, or it could also lead to something like subsidence phenomena, where the ground simply subsides. Both of these can be quite catastrophic with huge economic consequences. This setting of subsurface also tells us a bit about the kind of applications which involve the coupling of flow mechanics and fractures. Indeed, the inducedearthquakes.org is a website that tracks the different processes that lead to induced seismicity, and the two main contributors are the fracking and mining, contributing mostly around 58% of the total seismicity. But also there are lesser actors in this. Now all these earthquakes, these induced earthquakes are taking place in the subsurface, but if it becomes bigger, that can have quite a consequence. And they are all results of the coupling of flow and mechanics in the subsurface. In fact, if we look at the subsurface, we see a combination of two factors. One is the processes, and in the processes, I have thermal, hydrological, chemical, mechanical. They are typically called THMC, and they are often influencing each other in a fairly non-linear, non-trivial manner. At the same time, you also have geometric complexity, and that is evident in terms of these small fractures and some big fractures. You have a network of these fractures, and very heterogeneous material that is there. So you have this structure and you have the processes, and they are both interacting together, and that makes the whole description pretty complex. I am a member of Center for Modeling of Coupled Subsurface Dynamics, led by Inga Bere, where we are trying to study some of these phenomena, and that's the kind of setting I'm going to have. Now, in this work, I'm going to only restrict myself to the fractured media and the flow and the coupling of flow and mechanics. Now, let me motivate why this is an interesting and important problem. We see, this is from this reference, we see that you have this fracture, and around this you have a damaged zone. And around it you have this host rock. And if you look at the permeability field, then you see that the permeability is increasing a bit in the damaged zone, then somehow decreasing quite a bit. And then again, depending on whether you have symmetry or asymmetry, again increasing. In other words, you have quite a heterogeneous permeability field around this fracture. But perhaps more striking is the mechanical effect. Because in mechanical effect, you have the host rock, which has, a good amount of Young's modulus. This is the Young's modulus. But as you go closer to the fracture, you really have a decline in the yield stress. And that means that the fractures are really the location with the maximum vulnerability for mechanical instability. So those are the places where the mechanical instability may happen. Now, there is something more happening when the fractures and the flow and the mechanics are present. So first of all, the fractures are the primary conduits for the flow. So the flow typically, passes through the fractures, and they really influence the flow quite strongly. But something more is there. When we have flow and mechanics and fractures together, it turns out that the flow in the fracture that reduces the pressure in that flow, that reduces the compressive normal stresses. And when these effective normal stresses are reduced, then you can immediately think in terms of the physical situation that if these compressive forces are reduced, then it becomes much easier to sleep. Or you can apply Coulomb's law to see that. So what happens is that in case of fractured media and flow and mechanics, the chances of sleepage is increasing, not just because of the fracture, but also because of the flow that is present. And the flow is, so this coupling of flow, mechanics, and fracture, to me, it's a vital coupling, and it's an important coupling to study. And that's the motivation for studying this problem. Now, in our setting, what I'm going to do is to study the fractures as surfaces. So we will have a fracture surface here, which would be a 2D surface embedded in a 3-dimensional porous matrix. And I will come to it a bit later. Now, this whole area is, known as what we call poroelasticity, poro standing for the porous. And there are two founders for this field, which are people who founded this field, Terzaghi and Biot. So Terzaghi was the one who started it, and Biot gave it a nice, foundational framework to do further studies. And that is why we call these equations as the Biot equation. And this Biot equation basically couples the flow and mechanics. Now, if I were to ask you, to those who are not into this Biot business, if I ask you, what do you think? And when you think of mechanics equation, you'd say, well, either the elasticity equation or the elastic wave equation, and for flow, you would say, okay, it could be some kind of a Darcy equation, which would be an elliptic equation for the pressure, or a parabolic equation if you have some compressibility. And indeed, that is the situation. But now we also have coupling. So what is this coupling doing? So in coupling, you see these are the red terms. The stress in the porous matrix now gets modified due to the fluid pressure. And this fluid pressure is coming up in the poroelastic stress. On the other hand, when we think in terms of the flow, the solid skeleton gets deformed due to the mechanical deformation, which changes the porosity. And the divergence of U gives you some kind of a change in volume. You take the time derivative, gives you the change in porosity. So these terms, after some linearization and so on, you get this term which accounts for the change in porosity. And you see the coupling of pressure here in the mechanics equation, the equation for displacement U, and in the flow equation, you get a coupling from the displacement. And this forms what we call a BO model. Sometimes this time derivative is dropped in the mechanics equation, then we call it quasi-static BO, and so on and so forth. The unknowns here are the pressure, displacement, and flux if you write it in this mixed form. Now, there has been a lot of work on BO, in terms of well-posedness. Showalter was the one who gave the first results in this direction. English and Wheeler, they did it following a bit of homogenization type of argument, and further extensions in terms of nonlinearities and so on, discretization, temporal discretization, solvers, iterative coupling, extensions. And I would just mention that, while I was talking more on the subsurface in terms of applications, you see a lot of names here: Maria Rognes, Kent Andre Mardal, Johannes Kraus, Maria Limbri, Raja Shekhar. All these people are working quite a bit with Paulo Zunino, Yotov. I mean, they are working quite a bit on the biological side of this BO-type model. And in fact, there is a conference every 4 years or so, which is on the BO-type equations. So it's really has grown up as a field now and attracts a lot of people from engineering, mathematics, and so on, spanning a wide variety of applications. And I am just putting here some names, but there are much more, and I apologize for omissions here. So that takes care of the coupling of flow and mechanics. Now to incorporate fractures, as I said, I'm going to basically denote them as surfaces. But of course, the true fracture has some finite thickness. And what we have to do is essentially collapse this finite thickness into one surface. And this is the description I want to have, because, well, resolving this thin domain is going to be extremely expensive. At the same time, these fractures are too big to be absorbed in just defining an effective hydraulic conductivity, and they really have to be explicitly accounted for. So the compromise or the right approach is then to think in terms of a surface here. And if you look at the fracture flow model, what you see typically is that you will have a flow model with some source terms in the matrix. On the fracture, you will also have one other flow model on the fracture surface. But then on the right-hand side, you will get a jump in flux from the matrix side. And you can imagine why this happens, because of course you started with a thin fracture and then you collapsed it. So the flux from the two sides of the matrices, they will now appear on the surface and then appear as the jump in flux term and will appear as the source term. And then you have to put some interface condition. So the continuity of pressures, you put it, and you can have more fancy models and so on. Typically for the flow model, I write down a single phase incompressible Darcy model, which is just an elliptic equation for the pressure. But you could have two phase, you could have, slightly compressible and so on. So you can choose your flow model, but the larger structure is going to be of this type. There has been a lot of work on fracture. It's a huge business. Last time in the SIAM Geosciences meeting, I think I do not know how many sessions were being organized on fractured media. So there were there has been a lot of activity in the fracture. There is a review by Inga Bere and Florian Doster and Eric Scheile-Gavlan, a recent review, which gives a very friendly introduction to the kind of models. All this literature that I'm giving here is mostly on the modeling of this flow in a fractured medium. We also did some work on that, and we basically took some kind of approach of compactness arguments to derive starting from this epsilon model and collapsing it on an interface by thinking a problem as a sequence of epsilon problem and then studying the limit problem. With Sebon and Janot Bolton, they have been developing a framework to study, the fractured medium with, these problems are called like mixed dimensional models, and they are trying to develop a framework to study that. But they're really, I don't have time to discuss, but all the references that I have given by a lot of people are the kind of references we all study in order to understand what is going on. And as I said, this is only, I am not discussing the numerical part and the computational part, which is a full field in itself. So this is just for pure modeling. So now that we have a fracture model, we have a BO type model in a matrix. It's not too difficult to put it together. And indeed, the model for the fractured medium for the couple flow and mechanics is nothing but a BO type model in matrix. Of course, you have to have some interface conditions on the fracture, but it is just the BO model. And you have a flow equation in the fracture, and you see that I get a leakage type term, this jump in flux term that I was mentioning before. You see also appearance of the width term in the fracture equation. The width is more like a jump in displacement. It's not really that. More like it is the change in width would be the jump in displacement. But you take a time derivative, so it does not matter. Now again, this width appears because you have collapsed it. So you can imagine that in the storage term, I would have the appearance of the width coming up. Now for the flow equation, you see the coupling appearing everywhere. You have the width coming from the displacement. This permeability of the fracture typically is taken as the cubic law. And the cubic law, again, is this width, which in a nonlinear situation, if you take it as a true nonlinearity, having this jump in the width, jump of the displacement, that will make it very difficult. But you see the coupling here with all these variables together. So that's the setting. Recently, there has been a lot of work on this coupled fractured geomechanics flow coupling. Interestingly, all these references, actually, none of them are more than 10 years old. And most of them actually are 4 or 5 years old. So there has been really a lot of activity in this field. And there are good reasons why this has attracted a lot of attention recently in many ways, from application side, from mathematics side, and so on. So what are the main results that I am concerned with here? So one is, of course, the existence and uniqueness questions for such models. You can ask, is it just a purely mathematical interest? Well, that is not too bad. but I would say there is more to it. First of all, when we are discussing these existence uniqueness questions, we would be doing mostly with the Galerkin type approximation. So that also gives you a numerical method. And also for doing computations, you would like to see that what you are computing has a good, good basis to it. So this question is not merely, at least from my motivation, it's not merely a purely mathematical exercise, which is also nothing wrong with it either. Then I would go to developing a bit of iterative schemes for these coupled models. Again, what are these iterative schemes? Well, you can see that I have flow equation, I have mechanics equation, I have fracture flow equation. Now, should I solve it all together? Should I sequentially solve it? Should I, iterate at each time step and so on? There are a lot of questions which all fall under the purview of what we call iterative schemes. Multi-rate schemes are, again, coming from the fact that we have different equations and different physics. So if I have mechanics equation and the flow equation, it is not always the case that the characteristic times would be the same in both the situations. So, sometimes the mechanics response may be much slower than the flow response. And in that case, you would like to have multiple flow steps for each mechanics step, because then each mechanics step solving is, it's just a computational cost. So this kind of it forms a natural setting for what we would call a different time stepping for different physics. And then there would be the extensions, but I won't touch that. So these are the three topics that I'm going to be discussing here. So now I have just put it together, this whole model. This is just as the same as the model I already described. If you don't want to remember all this complicated equation, just say that this is a flow and mechanics BO equation in the matrix coupled with a surface equation on the fracture. That's basically the setting. The rest is all looking too complicated, but it's not as complicated as it looks. I should mention the primary work in this was done by Vivet Giro and Mary Wheeler and Ben Ganis and Mark Meyer, who analyzed this model using a conformal type formulation. We extended this work together with Vivet Giro and Mary Wheeler and Gurpreet Singh, where we did a mixed type setting. But this was all done when there was no time derivative. So it was all done for the quasi-static BO case. And what we have been doing recently is to extend it when we have considered the elastic wave with Martin de Hoop from Rice University. And we have good reasons why we would like to have that. I would just mention the kind of difficulty or the peculiarity of this analysis or in this study. So, of course, the first question is the kind of spaces that we should be having. Now, because we have a jump in displacement, we cannot have an H1 in the whole domain. So what we will have is an H1 in each of the subdomain omega plus, omega minus, which are the two sides of the fracture. And then you can just define this this Sobolev space, so that's not too bad. So the displacement is going to lie in this space, which is in H1 omega plus and H1 omega minus. But now there is something more. As I said, the permeability in the fracture is a function of width. Now we would assume this width to be given function both in space and time, and we would have some asymptotic behavior for the width, but this also goes to 0 at the boundary. So now you see that in the permeability, going to 0 at the boundary, I'm not going to get a full H1 type business on the fracture surface, but I must contend with these widths. So I'm going to have some kind of a weighted space there. And indeed, I would have for the fracture pressure, I would have some kind of an H half in for the pressure, and some kind of a weighted gradient in L2. This H half comes because we have assumed the continuity of the traces with the matrix pressure. So the matrix pressure will be an elliptic equation that will be in H1. So the trace will be in H half, and then you would have this weighted L2 type setting for the gradient. And then you can define this this norm, and you can show that it's a good space, it's a Hilbert space, and you have the density and the separability and all these properties. So that's a bit. So choosing the space, I would say, is the key question here. And once you have the space, then you can have the pressure in the H1 and pressure on the fracture in this weighted type space that I just had, and then you can define it together, make a product space, and then with this Q, you get again a nice separable structure, and also having some extension properties. And with that, basically you have everything prepared. You can show that you have a unique solution. The idea is through Galerkin approximation and getting a compactness estimate, showing that it has the sequences have limit, and this limit satisfy the equation, and so on. So that's basically the idea of the well posedness. Now, let me remark on what I would call the deficiency of the model that I just discussed. If you see, I have accounted for the fracture flow model. And I would say that's a good enough description, Okay, there is a continuity of pressure, but you can make that. That's not too bad. But in terms of mechanics of the fracture, it's very poor. In fact, it does not even know that the two sides of fracture can penetrate each other. There is no mechanism to stop this from penetrating into each other. And therefore, we would like to have a situation where, this penetration is somehow repelled. And we are motivated by the model from Oden and Martins, which motivated by the models from tribology, tried to somehow resist this penetration, and this model now we have in the context of poroelasticity. And so we add this extra term, which is a nonlinear term. And once we have that, then then again one does the analysis, and this is a work that we did with Martin de Hoop from Rice, as I already mentioned. And you see already in this, you see that the time derivative now is helping me, in the sense that I am getting now, I can extend the models, make it more richer, get the slip velocity and everything when I have the time derivative in my elasticity equation as well. And also here the interest is more from the seismicity side. So it makes sense to have that elastic wave type property. So again, you can show the well posedness, and we can then further extend these models. Okay, so with that, I would move to the next part, which is the iterative schemes, are also called the sequentially coupled schemes. And let me start with the BO type equation, which is a bit simpler to follow. Now in the BO, you have, well, two equations. One is this flow equation, the other is mechanics equation. What's the easiest way? Well, the easiest way would be, or the most straightforward way would be to just discretize in time, also in space if you want, and then just put it all together and solve it all together. that approach, of course, would be called a monolithic approach. But there is a good reason why one would like to decouple the two equations. And those reasons have something to do with the fact that, first of all, you may have very good solvers for flow and solvers for mechanics. And you would like to take advantage of these specialized solvers for each of these physics. And if you decouple them, then you have precisely the situation where you can take use of that, you can make use of that advantage. But the second argument is more practical. Typically, you have legacy codes for solving for flow, legacy codes for mechanics, and you would need to, couple them or have, and you don't want to throw everything that you have, but you want to still make it work. And in that situation, well, if you decouple it, then it is just a matter of sending data from one code to the other and so on. And that is also a very practical reason why one uses this splitting type schemes. Here, here I am mentioning this scheme called fixed stress splitting, which means basically, freezing what we call a mean stress. But I won't go much into the discussion of this. I would just mention the following way of writing it. So this is your flow equation. In the flow equation, you have taken the displacement from the previous iterate. N is the time stepping here, and I is the iterate here. And this iteration is taking place at each time step. Now, all I have done is to add this red term, which is the L times the previous iterate minus the current iterate. And it is this term which is an addition that is being done in this fixed stress splitting. Now, the reason why I wanted to write it with L instead of a fixed constant that is used in the fixed stress splitting is because just writing L gives you a bit of psychological feeling that you have now the freedom to change this L. And indeed, that is true. You can play with this L. And once you have chosen an L, and we will come to it, how to choose, then you solve for this Pni plus 1, and then you solve for the mechanics equation with no change. You can see this as some kind of a Gauss-Seidel type operation, block Gauss-Seidel type operation. Okay? Or if you think in terms of Schur complement. Now this L, indeed, you can choose what is the standard for the fixed stress, which is this L physical. KDR is defined here. It is basically coming from the lemma parameter. This is the dimension. But one can prove that actually you don't really need this L physical. You need just half of it. And indeed, Miklich and Wheeler, almost, it's not exactly the way they proved, but almost the result is that you get a contraction because this quantity is strictly less than 1. And this is these E's are the difference in two successive iterates. And, so you get a proper contraction for L larger than L min. And then there have been extensions in different ways. And you can play with it, make it partial in time, and so on. So we made this different type of extensions. I won't discuss the undrained split scheme. That is when you regularize the mechanics equation, but leave the flow part unchanged. And you can come up with different schemes, as I said. Now, these choices of L, so Miklich and Wheeler, they called it optimized fixed stress. And choosing half, because of course the low L you choose, the smaller is this contraction coefficient. So that gives you a feeling that the convergence will be faster for the minimum L that you should choose, but not too less than that, because then you won't have convergence. So to us, it was a natural question to see whether is this really L min is really the optimized one. And here, optimized one, we define in terms of the lowest number of iterations for a fixed number of time steps. for different choices of L. And indeed, in this investigation, what we saw was that actually it is not L min or L physical which is the optimal, but it is somewhere in between the two. And this dependency is not too easy to characterize because it depends on, this beta, which is somehow coming from how the Laplace norm estimate, how the H2 norm is estimated by the Laplace norm, and so on. So it depends on the geometry shape of the geometry constants. So I think it is nice to see this in a picture. So we did some solve a Mendel's problem in 2D by taking different stabilization parameters. And you see that the optimal is lying in between the L physical and the Miklich and Wheeler L, or the minimum L. And this holds true for different discretization. In fact, the discretization is almost immaterial in all these calculations. And I will come to that. In fact, this discretization, the fact that it is immaterial, tells you something practical. Because this beta, it depends on the shape and so on. So how to determine this L optimal? Of course, I'm not going to solve for different L just to find which L solves it the best. That is, of course, an overkill. But what I can do is I can take it on a very coarse space, and on this coarse space I can just solve it, and optimize it there. And I know that it is agnostic of the discretization, the mesh size, and therefore, these things will work also with finer discretization. So that is a brief journey to this splitting schemes. But recently, in this PhD thesis of Jakub Both, what he has done is he has looked at the sequential schemes from variational point of view. And indeed, you can look at as a sure complement approach. So you have these continuous operators, you discretize it, you get it in the discrete space. But then when you apply the sequential schemes, essentially, you are solving first the flow problem by decoupling it from the mechanics. So taking some kind of sure complement and then solving the mechanics equation. Now, this approach of solving flow and mechanics motivates you that, there is some kind of minimization problem also is at hand, because you have two variational problems together, which are coupled together. So, you then can think of some kind of an alternating minimization that is happening. And indeed, Jakub defined a gradient flow approach to this BO model. And once you have a gradient flow formulation, you can look it as the minimization. And you can look at the dual of this energy, and then you can minimize. So you have different choices. And once you have this free energy, so it gives some kind of a degenerate structure for the gradient flow formulation. And when you do this alternating minimization, first for the flow and then for the mechanics and so on, you can show that this alternating minimization actually is nothing but what is popularly known as the undrained split. Or you can do, you can make a dual of this energy and then do this minimization, and that comes out to be the fixed stress splitting. So now that you have put it in the convergence framework, it becomes pretty easy to use your convex optimization toolboxes to extend this to, different equations and so on. Now I will just briefly touch in the next 2 minutes on extension of this to the fractured medium, because all of this was just for purely BO, but now we have a fractured medium. How do we extend this? Well, what we did was, again, this L, helps in thinking. So I have a stabilization parameter in the flow equation. I can also have a similar stabilization parameter, I call it gamma C, in the fracture, in the crack surface, the C denoting the crack. And so I solved the flow equation together for the fracture and for the matrix with stabilization parameters which are different. And then I solved the mechanics. So this is the extension of fixed stress type splitting to the fractured case, except that I do not know what this gamma C is. And once I know, then my scheme is determined. So how do I determine it? Well, the idea is basically to look at the equation satisfied by the two successive iterates and try to study to make sure when you have a contraction, and in this case, you have to define composite quantities of the pressure and displacements, same for the fracture, and you can then show contraction. The interesting thing is that more than the contraction, so of course we have the contraction, but what we also see here is this appearing of some kind of a condition, and the C star is coming from this elasticity constant and the Poincaré constant and so on, which tells you that basically the shape of the fracture is also going to be important in how well this algorithm works. And that is a question that we have not explored, but that is an interesting question, how the shape of the fracture comes into picture. I will conclude by just mentioning the last part, which is the multi-rate schemes. Now, as I said, in the multi-rate schemes, I have a flow equation, I have a mechanics equation, and then the natural question is, should I take the same time step for the flow or as I do it for the mechanics? The answer is, of course, if you have an iterative scheme where you have decoupled it, then you are free to choose your time step for each of the equation. Of course, then there would be a lot of questions. How about the convergence? How many time steps of flow I can take for each mechanics step? What's the computational efficiency? In practice, what people do is they just solve a flow equation and once in a while solve the mechanics equation and update, the displacement or the divergence of the displacement in the flow equation. And that we call it an explicit scheme. So if we do an explicit scheme, how many times can I take the flow steps and so on? I would not have time to discuss any of these questions, but I would refer to work of Tamim Almani in his PhD thesis, where he studied a lot of these iterative schemes. We were doing it together with Wheeler and with Mary Wheeler and myself, and also other collaborators with Vivek Jiro, Ali Dogru. So there has been a lot of work which we have done on these multi-rate type schemes. I'm just mentioning here my own works, but there are a lot of multi-rate type schemes also used for other type of settings which I'm not mentioning. So again, just to mention that the single rate versus multi-rate is when you take different time steps for flow versus mechanics, that is the multi-rate, and just one time step for each physics is the single rate. I will just conclude by mentioning here this CPU run time versus simulation for one of this standard problem. I think it was for the Bradley problem, where we tried to study this multi-rate and the time savings and so on. And of course, the maximum time you save is when you are doing explicit coupling with a multi-rate where you take 8 flow steps for each mechanics system. And if you do that, of course, you are solving flow mechanics only 1/8 of the time as you would have done if you would have done at the same time step. On the other hand, the maximum time is taken when you are taking the same time step for each flow and mechanics and then iterating between the two. And that, of course, is taking, so you see the difference is like 5 times or so, maybe 4.5 times between these two. And then you can design a lot of different options of when to iterate and so on and so forth, which would give you something in between these two extremes. And with that, I will conclude by just mentioning that this is, I find it a very organic problem with a lot of questions appearing. The tribology considerations motivate you to consider a geotribology type of field, where one would like to use some ideas from tribology and put it in understanding the fracture mechanics when the fluid is also present, and then of course developing, you know, all around of computational and mathematical tools around it. So with that, I would just stop here and thank once again the organizers for this very kind invitation, and I'm ready to take questions. So thank you once again.
Thank you very much, Kundan, for the nice and very interesting talk. Now it's time for questions. So I encourage the participants to post their questions in the chat. We don't have yet any question, but I can start with some questions that I have. For example, I was thinking about, so you were talking about the solution methods, in particular about the iterative coupling methods, but you didn't comment much on discretization techniques. So are there any restrictions, or can you comment anything on this, or are relevant for the choice or for the development of the iterative methods, or?
Okay, so I would answer this in two parts. One is in terms of the discretization of these equations themselves, and of course that is a delicate question because you have different equations, and you have coupling. So what kind of you know, spaces, what kind of finite element spaces to use for each of the variables? That indeed is an important question, and there has been quite some work on this discretization part, and I did not touch on any of it. Now, in the iterative schemes, when we are discussing these iterative schemes, I did not mention the discretization because these iterative schemes turn out to be quite agnostic to the discretization method itself. And the reason is that when we look at these equations, we can think in terms of operator splitting itself. So think in terms of the two mechanics and the flow operator themselves. And then these two, and you can show that there is a contraction or the stability is there on the operator level itself. And because this is at the continuous level itself, it automatically gets translated to the discretization, more or less any discretization that you use. So from that point of view, the discretization is not so important when you discuss these iterative schemes. But there may be a finer question here, which is that the discretization itself may add some, some viscosity to the problem. And if that is added, then maybe, this contraction will be even faster, or I may not need this stabilization parameters as big as I am taking, and so on. And that would be dependent on the discretization, and that would require a careful investigation of the discretization process itself.
Okay, good, thanks. So, and also regarding this splitting method, so you presented these methods first for Viot, but in Viot you choose the two-field formulation with the pressure and displacement, but we have different formulations, right, with the different unknowns, and also I assume that these formulations can be used in the fracture model. So are extensions, or could be these iterative methods extended to these other formulations?
Yes, in fact, for this, again, for the 2-field or the 3-field, at least I have done it for 3-field and 2-field. For this, I did not find any difficulty in developing iterative schemes. But I saw that when you do multi-rate schemes, then you see the difference. So then it matters how you do the mixed, whether you are doing it in the mixed setting or 3-field formulation, or you are doing it in a 2-field formulation. And there you start seeing these differences appearing. Or also in the case of heterogeneity, this starts playing a role. So there it starts mattering when you try to localize this stabilization parameters, and then it starts playing a role.
Okay, I understand. Good. Okay, we have a question in the chat. This is from Gabriel Varela, and well, he thanked you for the insightful talk, and he was wondering if there are any results on poroelasticity accounting with intersecting fractures. If there are results, if the results that you showed are extendable in this case to that case.
Yeah, so I mean, at least in the discussion I presented here, I have not considered the case of intersecting fractures, but not Barton and Witze and Bone, they have been working on extending this framework where the co-dimensions are not a problem. So there, that framework can take care of this kind of intersecting fractures too. Also, there have been works from the French group recently. I should mention this, but okay, this was in one of the references where they have been also considering this kind of intersecting fractures and poroelasticity. So there have been some extensions in that, but not in the work that I presented.
Okay. Good. So there are. Okay, I don't see any other questions. So maybe I can ask another question, like maybe more general. If so, you were talking about a setting with a lot of multi-physics, different physics coupled together, complex setting. And I think this is a source of very nice problems, right? So could you comment a bit more on this, about the problems that appear regarding this multiphysicity that we have?
Yeah, so I would claim that in this subsurface business, with the fractures, with the with heterogeneity, and this combination of complex processes appearing, I would say it's a very organic source of problem. In the sense, I mean, just to put example, so I had these multi-rate methods, I had iterative schemes, and I have biotype, and then I have fracture type. So now, of course, you can put it all together. You can take one iterative scheme. You can work with multi-rate for one iterative scheme. You can work with fractured setting in a not fractured setting. You can try to include a bit of thermo poroelasticity, or have effect of transport or of concentration, reactions. The thermal effects could become quite important in geothermal type of settings, because then the fluid, even a small increase in temperature leads to a lot of stresses because of the thermal stresses that get built up. So in that sense, there is a lot of physics that is involved, a lot of activity that can happen, and a lot of coupling that is to be taken care of. At the same time, I would say that we should also evolve some way of figuring out which are the effects that are the most important effects occurring in a particular scenario, and then trying to work that out, so have a methodology to identify the most important physics that is at at work, maybe through some kind of non-dimensionalization, maybe through some numerical experiments. I do not know. I do not have the full picture of it, but that would be a good way. And then think in terms of which coupling is the most important one, and then work on that in this setting. And also, I mean, just another example is I have considered everything is a static fracture here. And of course, this fracture can, get ruptured. And there have been people working also in Bergen, but also in Thomas Wick and Mary Wheeler and Miklich and also other groups. A lot of work of Peter Bastian. So a lot of people are working on, on the work of Mihe, of course, where they have been trying to consider the fractures when they are propagating. And that is again, that is another level of complexity that can have. So it's really a lot of complex issues. And I think identifying which one are the most important and working on that, I think, is already a very nice source of problems.
Yeah, of course, you can, add many things, right?
Yes.
Yeah. So, okay. So in the chat, we have another, well, it's a comment. Robert Bird, thank you for the talk. And well, it's 2 minutes left to 5. So I think we can stop here because the next session starts at 5. So I would like to thank you again for the great talk. I like a lot, and you offer us a lot of possibilities of problems, very interesting problems. So thanks a lot for the talk again. And also I would like to thank to the attendees. And I want to remind that for the parallel sessions, you have to access by using the platform. So if there is any problem, as this morning, we will have a Zoom link, but if not, we can access as usual, as planned, okay? So thanks again, Kundan.
Yeah,
and
thank you very much,
well,
Carmen. Thanks
see you around.
And thanks to the organizers.